All right, let's dive right into this explainer because we've got a truly incredible story lined up for today. We're going to look at how fixing a really mundane, super frustrating industrial problem accidentally birthed the entire foundation of modern astrophysics. It is literally the perfect example of how chasing precision in one tiny field can just blow the doors completely off our understanding of the universe. Now, how does an orphan trapped in a collapsed building unlock the secrets of the stars? I know, it's a super dramatic hook, but the journey of Joseph Fraunhofer literally begins in the rubble of a disaster in Munich. It honestly sounds like a movie script, but this one single event in 1801 set off a chain reaction that took humanity from looking at blurry stars to actually decoding what they are made of.
Section 1. From Rubble to Precision.
To really get the science we're going to unpack here, we first have to understand the ticking clock of 19th century industry that drove the whole thing. See, Fraunhofer had lost both his parents by age 12 and was stuck in a pretty restrictive apprenticeship. But surviving that 1801 building collapse, that actually connected this young apprentice with Bavarian entrepreneurs. By 1806, he's working as an optician. Come 1811, while he's still in his 20s, he's directing this massive glass works at Benedict Beauharn. And look, they didn't need a pure philosopher of light. They desperately needed dependable optical glass for surveying and astronomical instruments.
Which brings us to Section 2. The problem with cheap glass.
You see, Fraunhofer didn't jump into this field trying to unlock the cosmos. He was just trying to fix a very practical, highly relatable manufacturing flaw. Anyone who's ever looked through a cheap magnifying glass or, a terrible smartphone camera filter has seen this. It's chromatic aberration. Basically, glass bends blue light more than red light, failing to bring every color to the same focus. The result? These colored fringes and just a blurry mess of an image.
The 19th century industrial fix for all that blur was the achromatic doublet. You essentially pair a simple converging lens with a diverging lens made of different glass to cancel out those color-dependent errors. But here's the catch. To actually manufacture this at scale, a workshop needed ridiculously precise measurements of exactly how strongly each glass bent light and how that bending shifted by color. So how do you measure the exact bend of a specific color when something like yellow is just a subjective guess? This was a massive roadblock. Yellow is way too broad. Its boundary totally shifts depending on who's looking and what the lighting in the room is like. The real paradigm shift happened when Fraunhofer realized he couldn't rely on human eyesight and artisanal trial and error anymore. He needed an objective, physical standard to test his glass against.
Section 3. Mapping the sun's shadows.
That purely practical necessity led Fraunhofer to use sunlight as his standard, and doing that revealed something completely unexpected. Spreading sunlight with a prism to get a rainbow wasn't exactly new. In fact, in 1802, William Hyde Wollaston actually saw these dark lines in the solar spectrum. But Wollaston kind of just thought he was seeing boundaries between colors and moved on. Fraunhofer's genius wasn't just having sharper eyesight, it's that he mapped these fixed dark marks to create a highly accurate measuring system. He transformed a passing observation into strict metrology. To pull this off, he deconstructed things and built this brilliantly simple, room-sized angular comparator. Step 1. Sunlight enters a dark room through a remarkably narrow vertical slit. Step 2. A collimating lens makes the light rays perfectly parallel. Step 3. A prism separates the colors. And finally, Step 4. A telescope mounted on a precise theodolite dial records the exact angle. Now that narrow slit is the absolute game changer here. A wide window creates overlapping light that washes out the shadows, but using a slit just 0.6 of a millimeter wide prevented that overlap, revealing these incredibly fine dark marks. And he tested this relentlessly by comparing sunlight with lamplight and swapping out his prisms. He proved these marks were consistent features of sunlight, not just scratches on his gear. He actually counted around 574 distinct lines just between his reference marks, B and H. He gave the strongest lines letters, so opticians anywhere could reference the exact same narrow landmark when testing their glass. Moving on to Section 4, decoding spectral lines. So the sun had officially become a ruler for testing glass. But for the sake of this explainer, we really need to understand what these lines actually were. A spectral line isn't a black thread literally drawn on the light. It's an actual deficit. It's a narrow interval of wavelength where an instrument records less light than it would from the surrounding spectrum. If you picture it on a graph, it basically looks like a dip compared to the local background.
And these dips have three distinct properties we care about. First is position, the exact centered wavelength. This was Fraunhofer's go-to for marking coordinates. Second is strength, meaning the total amount of light removed across that dip. And third is width and shape, which shows how that deficit is distributed around the center. Now, Fraunhofer couldn't fully decode all these modern physics properties yet, but he provided a stable, measurable feature with distinguishable traits that later physicists would absolutely rely on.
Section 5. Building an absolute ruler. But there was still one major fundamental problem. Prisms separate color based on the specific glass they're made of, which means the scale itself was flawed. If your ruler is made of the very material you're testing, it's relative. So in 1821, Fraunhofer pivoted and created diffraction gratings. He literally stretched 260 fine parallel wires across a frame using a screw thread to ensure flawless spacing. When sunlight passed through this array, it produced a rainbow without a prism at all. It relied purely on wave interference, where crests and troughs of light waves either reinforce or cancel each other out.
This brilliantly illustrates a massive shift in the history of science. We go from a relative ruler, the prism, which is completely dependent on the unpredictable dispersion properties and material flaws of glass, to an absolute ruler. The diffraction grating depends solely on an engineered, mathematically consistent physical distance. It converted wavelength into pure math. And in this amazing historical coincidence, right around 1822, while Fraunhofer was manufacturing these gratings, Joseph Fourier in France published his mathematics of heat. Now, Fourier wasn't studying light, but his math provided the exact theoretical cheat code needed to decompose complex variations into simple periodic waves. So you have the physical tool built in Germany, the exact mathematical language published in France, and the stage is perfectly set. Section 6. Matter reporting on itself. Now, what's really interesting about this next phase is how Fraunhofer's industrial tool accidentally opened the door to the cosmos. See, sunlight reflected off the moon or planets kept the exact same pattern of dark lines because the sun was still the source. But when he pointed his highly precise instruments at the stars, he realized the patterns changed. He proved that starlight arriving from these unresolved points in the night sky carried completely unique, reproducible internal signatures. Starlight didn't just reproduce the solar pattern. Matter was quite literally beginning to report on itself from across the galaxy. Before his early death at just 39 years old in 1826, Fraunhofer's trajectory was nothing short of incredible. He went from an uneducated orphan craftsman in 1801 to a fully recognized professor. He earned an honorary doctorate and was even ennobled by the Royal Bavarian Academy. His strict industrial manufacturing had literally forced elite academic institutions to recognize a completely new source of exact knowledge. The crucial takeaway here is that he made the evidence stable enough that a later inference could be compelled. Fraunhofer didn't know the chemical makeup of the stars. He didn't know about quantum energy states. But he didn't just leave behind an unanswered observation. He separated the variables. He built a rock-solid, stable foundation that allowed later astrophysicists to discover the truth. So, I'm going to leave you with this thought for our explainer today. What kind of matter removes selected wavelengths from broad sunlight? And why do these exact same lines return in our modern laboratories across the universe? It is absolutely wild to think that the very terrestrial quest to fix a blurry magnifying glass gave us the ultimate decoder ring for the entire universe. It really makes you wonder what mundane problems we're solving today that might unlock tomorrow's mysteries, right? Keep questioning, and I'll see you in the next one.